7,000 genes that you picked at your poster. Thank you so much. Okay, Maximilian?
There. Absolutely.
Great. So we continue with Maximilian Miller from Rutgers, and he's going back to the mystery samples of the Metagenomic Forensics Challenge, and we're looking forward to your talk. Thank you.
Thanks for the introduction. Hi, my name is Max Miller. I work with Jana Bromberg in the lovely New Jersey, and I have the first flash talk today about the CAMDA Metagenomic Forensics Challenge. And before I start, I want to first thank the organizers for organizing the track and the challenges, and especially for granting me a travel fellowship that I can come and present here today. So let's jump right in. For those of you who haven't been here in the morning, just a quick recap about the challenge. So what we get is 304 metagenomic samples, it's whole genome shotgun sequencing, from 16 known cities. What we also get is access to a database with soil samples. And now the question is, please predict geolocations of 61 mystery samples, which are also whole genome shotgun sequenced, but never have seen before in any of these cities. So in a great talk yesterday, I learned to make the audience or the user happy, lower the expectations a little. Let's do this. We did not use soil samples. Simply because we think that soil samples and samples which are taken from human-constructed environments are too diverse. We also did not predict geolocations, but bear with me, we still have cool results. All right, let's go back to last year. Those of you who have been in Chicago probably know this guy. That's Sheng Sheng, and this is his Al Capone hat, which he regularly wears at the lab now, because his approach last year based on mi-faser worked really well. The difference last year was that we had to predict unknown samples of cities which we actually already had in the training set. And the way we did this last year is we took our metagenomic samples and we ran them through our mi-faser pipeline. Mi-faser is a pretty fast and very accurate tool to do a function annotation of metagenomes just based on reads. And what you get from mi-faser is functional profiles. These functional profiles are essentially 1,200 dimensions long, is a 1,200 dimension long vector, 1,200 because our reference database, that's the amount of EC classifications we have in there. And for each position in this vector, you get the abundance of reads which are assigned by mi-faser to a specific enzyme classification. So basically every column here is an EC number, every row is a sample. So now we took these samples and we trained 8 SVM machines. 8 because we had 8 known cities, and so each city model predicts if an unknown sample is from the city or from any of the other cities. So now we ran our unknown samples through these 8 models, got 8 scores, ranked them, and said, okay, this is the most likely prediction that an unknown sample is from this model city. So the reason why this worked so well is we did 2 things. We balanced our training set because the input from the different cities was really unbalanced. And we had a random metagenome which we used to establish a threshold where we said, this is where we believe actually our predictions. So this year's challenge was a little different in the aspect that all the mystery samples were not seen before and not of any of the cities in the training set. So we simply asked, can we group the 61 mystery samples into the city of their origin? And to do this, we started in a very similar way. We took our metagenome samples and we ran them through mi-faser, created these functional profiles. And I remember it's 1,200 dimensions here. And then we embedded those 1,200 dimensional features into a low dimensional space, and we looked at it, in this case, 2 dimensionals. We used t-SNE to do this. And the distance here is reflecting how similar these functional profiles of 2 samples are. So here the sample 2 on the lower left is not as similar as the samples S1 and S3. So now having this representation, we clustered this using k-means to group these unknown samples into still unknown cities, but at least into cities where they belong together. As said, k-means, clearly we have to define which k. And to do this, we had to estimate K for K-means. Let me start or quickly go back to the embedding with t-SNE. I just want to point out that we did the embedding for all samples, the knowns and the unknowns, but of course the clustering we only did on the unknowns. So I said we had to estimate the K. To do this, we used the silhouette method, and silhouette score basically gives you an estimate of how good clusters separate, so how the objects in one cluster are similar than they are to any objects in another cluster. So we ran this, we estimated K with 10, and when we got the ground truth back, that's some weeks later, we were happy to see it's actually 8. So we were close. We thought it was 10 cities. The reality was it was 8 cities. And now let's look at the results. So this is the part where I put the expectations again a little up. This is the unknown samples in black, the known cities in gray, but they're just there for reference. This is the color coding of how the ground truth is, and this is how we clustered. So I'm not sure how good you can see this now, but there's actually some clusters which are very, very well in one color. And to make this a little more visual, in this plot you can see on the left the mystery cities, how they are in the ground truth, and on the right the clusters we proposed. And there's some things to note. First of all, you can see that things like Oslo or Santiago de Chile, they cluster really nicely. Things like Rio de Janeiro, which is a city I really love, is all over the place. To give you a number, the adjusted mutual information, which is a measure of how good the ground truth overlaps with our proposed clustering, is 0.561 would be a perfect fit. So, of course, K-means has the drawback that we have to estimate K, and there's other tools to do this better, and there is also tools which take care of that these clusters might be not as dense, so some might be more dense, some are not. And dbScan is a good tool to approach this, even if we run it with just default parameters. So if you do now dbScan clustering, you see that actually some of the clusters are even better than before. Right now we perfectly classify Oslo, or cluster Oslo, we perfectly cluster Santiago de Chile. And if you remember Rio before, which really messed up the plot before, here it's really nice, but you see it's much smaller. So what happens is dbScan labels a lot of these Rio, and it's actually 2/3 of them, as outliers, which leads to the adjusted mutual information going up, but it's actually just an artifact. So you could actually cluster Rio just by the outliers. This is already my summary. So what you see here, that we actually can cluster these mystery samples based on these functional profiles we create with mi-faser. Second, big cities like Rio, like cities where we have really diverse samples, clearly make it very difficult for us to group them. And last but not least, we think soil is not equal subway, even if you sometimes think in the New York subway you are in a dark hole at times. It's not the same, and we would really like to use this information, but we did not see how. Thanks. If there's any questions, let me know. I have a poster at Q09, and thanks to my lab, and thanks for the travel fellowship again.
Wonderful. Thank you so much for the brilliant talk. I'm sure there'll be plenty of questions at your poster, like whether you found any subgroups in your split-up clusters. I don't know, things that are a bit deeper in the hole or less deep. Thank you so much for the talk. We move on to the next flash talk. Let's go, Luis.